wipers, that does the door locks, power seats, and so on. But they don't deal with large power like the ones we deal with hybrid electric vehicles. As we saw earlier, the motor size is pretty large in the hybrid vehicle system. For example, in a blended HEV, you're looking at a 50 to 75 kilowatts electrical motor. In an extended range electrical vehicle, you're looking at a motor that is 125, 150 kilowatts. So those motors are fairly large in power ratings. Now, size-wise, they're not that huge as you might think. If you happen to go to the factory floor, and you might see electrical motors sitting somewhere driving a machinery. If you look at those motors, their size are very large. A 120 kilowatts motor in a factory floor could be so large that it's so heavy, it's fairly heavy. The reason for those motors to be heavy, there are two reasons. One is that those motors are operating at relatively low speed. A typical speed operating is 1500 RPM for 50 Hertz power supply and 1800 RPM for 60 Hertz power supply, or even 900 RPM and 1000 RPM, 1200 RPM, and so on. So those are fairly low speed motors. So therefore, they're pretty large. And later on, I'm going to show you that when you design a large speed, a high speed motor, the motor size can be significantly reduced. A second reason is that on a factory floor, most of the motors are air-cooled, which means there's no special design cooling system to deal with the heat generated inside those motors. Therefore, the size has to be fairly large in order to deal with the heat generated inside the motor. So therefore, you see those motors are big. But in a vehicle system, we have to consider the space available, and we don't want the vehicle to be too heavy. So therefore, the motors and the power electronics associated with hybrid electric vehicles are relatively at high speed operation, and their size are fairly small in comparison to the ones that you see in the factory in a machinery. However, we also have to deal with additional issues such as extreme cold and hot weathers in a vehicle operating condition. And we have to deal with vibration and shock associated with the vehicle operation, while those things do not exist in a factory, in a machinery operating. So the next section is going to discuss electrical drivetrain components for PHEV. Now those components are derived from the powertrain ratings. So which means you want to design a hybrid vehicle or PHEV, you will have to deal with what type of powertrain, what are the sizes, for the powertrain, the total powertrain. And then you can split them into an electrical motor and then engine. And then once you have the size of an electrical motor, you can decide what is the power electronics requirement, and then what is the system voltage and the system power ratings. How do you size the drivetrain motors? How big and what speed and what type of motors and so on. Once you know the size of the motor, you can size your power electronics. And then you can size your energy storage system based on your power electronics and motors, and then the basic powertrain driving distance requirement and so on. So you can size the energy and the power requirement for the battery systems. Okay. And then based on how much energy you have in your battery system, what voltage designed for the energy storage system, you may need energy management between battery and the motors. Okay, so right now what you're going to do is energy management converter is try to optimize the operating efficiency of the battery and the motor. At the meantime, you're also going to try to control the battery charge and discharge during driving the vehicle, whether it's motoring or whether it's regenerative braking. So you want to control the charging pattern so that the battery life can be extended. So you don't want the battery life to be shortened due to irregular charging, high frequency charging. So the energy management converter can basically do that function. It will help you to control and manage the battery, and therefore it will be able to extend the battery life. And then how to design the components, and then you may want to involve with some type of optimization algorithm to size the components for your vehicle system, so that you can take advantage. You can take advantage for the whole system design. Therefore, you can achieve a better fuel economy. One of the example is that we dealt with earlier today is the driving range for blended HEV, PHEV. If you design a 120 mpg vehicle, but if that 100 mpg only lasts for 10 miles, it does not help many people if their daily driving range is 20 or 40 miles. On the other hand, if you have a fairly decent MPG, but that MPG lasts for more than 80 miles, that's also not going to help somebody if his or her daily driving range is only 40 miles. So therefore, there is a coordination when you drive a PHEV, the equivalent electrical driving range, the range corresponding to the very high MPG for the blended PHEV. That makes a lot of sense. Now, on the other hand, if you're designing a range extended EV or a full PHEV, you may want to consider the option for customer to select between PHEV 20 and PHEV 40, so that they can choose the battery size that will suit their needs, daily driving needs, so that they can get the best out of the system. So those are the design considerations that we have to deal when we design a real vehicle system. So the propulsion system design itself is an iterative process, which means you're going to need a lot of iterations before you come to a concrete conclusion. And besides, a lot of the designs are not unique, which means the one that you design may be the best for your design criteria, but it may not be the best design if you select another set of design criteria. So often you will have to set up a cost function, which means what part of operating performance you want to achieve and which part you can compromise a little bit. So based on those compromise, and you can go ahead to design and optimize your system. There's coordination between electric and mechanical engineers, so that electrical and mechanical engineers, so that you can optimize not only the electrical drive portion of the vehicle system, but probably the mechanical and hydraulic and the vehicle itself design process. So the design again may take several processes and come back with a better design. And the size also may not be one unique solution. You may have a number of solutions that can satisfy different design criteria and different consumer expectations. Okay. When you go with your system design, the first step, as we said, is to determine the powertrain. Now, how do you determine the powertrain? We know that the powertrain needs to overcome a number of different aspects of the vehicle needs. One of them is acceleration. The rest would be hill climbing, also called gradability. And then acceleration needs, the rolling resistance, aerodynamic resistance, all those has to be overcome in order to drive the vehicle. So today we're going to stop here. We're going to continue tomorrow, continue with the powertrain rating and the components design, and we'll get into the rest of the presentations.